Hi everyone, I'm Adam Wolf-Gordon. I'm a senior engineer at DigitalOcean, and I work as the tech lead for our Kubernetes and container registry products. Today I'm going to share some updates about those products, but before I do that, I wanted to put them in context a little bit. You might have heard that Kubernetes and containers and many other things fit into the larger paradigm of what's called cloud-native software. So what does cloud native actually mean? What can it do for your software in your business? Those are the questions I want to answer before I talk about how the products that my team builds can help you do it. If you Google for the cloud native definition, you will find this very long definition from the Cloud Native Computing Foundation, or CNCF. I want to pick out some parts of it that can maybe help us understand what cloud native is all about, rather than just reading the whole thing. In the first paragraph, we get some examples of things that are cloud native. So containers, service meshes, microservices, immutable infrastructure, declarative APIs. Those all sound like great tools to use, and they are great tools. But I don't think looking at those examples really helps us understand what cloud native is, or more importantly, why we would want it. The more interesting part, in my opinion, is in the second paragraph. It says cloud-native technologies enable loosely coupled systems that are resilient, manageable, and observable. So resilience, manageability, and observability, these are really our goals. Those are the characteristics that can help our software to be successful and our businesses to be successful. And the key property that really helps us achieve those characteristics is this loose coupling. So just as a motivating example, let's say that you're building an online conference platform, like the one that we're all using today. The details of this app aren't really that important, but having an example will just help us talk about cloud-native software in general. So our application has a bunch of different layers or components. It has a web app that our users interact with, and that's backed by an API. Behind that API are all the features of the app. So we have some way for people to build a schedule for their conference. We have a video streaming component to manage the pre-recorded talks and maybe stream live talks, let people watch videos. We have a Q&A system so that you can ask questions and get answers to them, have a chat system so that people can interact with each other, have a social aspect to an online conference. We have a billing system that invoices our users. That's very important if we're going to make money on this. And we have an admin interface so that you can set everything up. You could build all of these pieces into a single piece of software. That's what we call a monolithic architecture. But remember, we were talking just a minute ago about loosely coupled systems. And there are a few good reasons why we want loosely coupled systems. First off is reliability. If the chat system crashes, people should still be able to watch their videos and build their schedules. So we want them to be independent in terms of failures. Second is scalability. Different parts of this system are going to have different loads, and they're going to scale differently. It's nice if we can scale them independently and choose which ones we want to scale up by adding more compute resources and which ones we want to scale out by adding more replicas. Third is agility. You might have different developers or different teams working on each piece of this application, and it's nice if they can mostly work independently and have their software talk to each other over APIs. So you might split your application into these microservices. Each component is now a separate piece of software. They all talk to each other over well-defined APIs. And this kind of architecture can help us with the problems we just talked about. We can isolate for failures, we can scale independently, and we can let teams work independently on their own pieces and make their own technology choices. The challenge now is we have to figure out how to manage and run all of these different components. They might be built by different people or different teams. Like I said, they might all be built in different languages or using different technologies. And they probably get updated independently at different times, have different scaling and resource requirements. So how do you manage all of that complexity? This is where containers come in as a first step. Each team can build a container for their service, and now all of our services are managed in a consistent way. They're all in containers. And the nice thing about containers is these all have their dependencies with them. So you're not managing different frameworks or different language runtimes. Those dependencies are all encapsulated within the container. Now that you have your container images, you'll want to store them somewhere, and that's what we call a container registry. Unless you're building something open source, you probably want a private container registry, one that only your team can access. This is the consistent way that we're going to manage our software. Every application goes into a container. They all get pushed to a registry. But storing these containers is just a prerequisite for what we actually want to do. What we actually want to do is run our software. So you could deploy these containers onto virtual machines. You don't need to have a VM for each container they can share. And let's say that most of our services are stateless, so we can deploy multiple replicas of them for resiliency and for performance. We'll deploy them across a handful of VMs. There are some challenges to this. One is you need to figure out which containers run where. You don't want to overload a single VM, and you also don't want to pay for a VM that's underutilized. If each team is deploying their services independently, they have to work together on this. The other struggle is I haven't drawn the communication lines on this slide because it would be a mess, but all of these services communicate, and we have to configure them with each other's addresses or implement some kind of service discovery. Again, each team is going to have to figure out how they do this with their dependent services. Finally, when we want to roll out a new version of a service, we have to coordinate that carefully. We don't want to take all the replicas down at once, because then we'd have downtime. And we want to make sure that we wait until the new instances are up and running and ready before we take down the old ones. These are all solvable problems, and we can solve them with traditional orchestration tools like Chef or Ansible. But encoding all of this knowledge of the system into those tools is kind of a manual process. They don't have a lot of primitives for us to use. So this is how we end up with Kubernetes. Kubernetes is a system for running containers. It's a container orchestrator. Kubernetes has a bunch of system components, which I've drawn at the bottom of the picture here, and it has some nodes to run containers on. The system components understand containers. You tell them about how you want your containers to run in your configuration. You tell them how many replicas, the resources they need, and any scheduling constraints you have, like they should be scheduled on the same node or different nodes from one another. And Kubernetes is going to make that happen. So at the end of the day, we still have containers running on VMs, same as we did before. Just now they're managed by a system that was built explicitly for this purpose. If you've used Kubernetes, and maybe even if you haven't used Kubernetes, you know that the idea is really simple, but the implementation is very complex. And one of those complexities is that making Kubernetes do what you want takes a lot of configuration. And all that configuration is written in this markup language called YAML. You have to update this YAML configuration as you update your software to roll out new versions and new configuration. And you probably have, say, a production environment and a staging environment, and they need slightly different configurations. YAML has really limited templating capabilities on its own, so you can easily end up with separate duplicative configuration for each of your environments and each of your components. One tool that can help us solve this problem is Helm. Helm is a package manager for Kubernetes. And what it really lets us do is template our YAML and manage it more easily. So we're going to write Helm charts. Their configurations are called charts for each of the services in our application. And we can share components between these Helm charts to handle any common concerns we have between our different services. And we can also use variables for any configuration differences like staging environment versus production environment. Makes it much easier to manage all of this configuration we have to do to run things on Kubernetes. So now we have our containers living in a container registry, and we have our application running in Kubernetes, and we're managing our manifests with Helm. This is all great. Our Helm charts are in a Git repository. In this case, I've drawn them in the same repository as our application code, but they could live in a separate repository too. We probably don't want to manually build our containers and manually deploy our application from our laptops or our workstations. We want some kind of continuous integration and continuous deployment to do that for us in an automated way. So a CI system is it's going to take our code, build it into containers, and push those containers to our registry. There are lots of different CI systems that you might choose, and which one works for you is going to depend a lot on your specific development environment. So I'm not going to recommend one here, but a couple of examples would be GitHub Actions or GitLab CI. And those are nice choices if you're hosting your code on those platforms. Regardless, whatever CI system you choose, it's going to take changes that you make to your application code, push new containers to your registry. When you have that done, you're going to update your Helm charts to look at the new versions. And you need some way to take those Helm charts and get them deployed into your Kubernetes cluster. That's what we would call continuous delivery or continuous deployment. And there are lots of tools for this again. In this case, I am going to recommend a specific one called Argo. Argo is a CNCF project, and it's Kubernetes native. So the nice thing about Argo is you can deploy it into your Kubernetes cluster easily, and it understands Helm charts, it understands Kubernetes, and it's a natural fit with the other tools that we're talking about today. Argo can also do various advanced things with Kubernetes, like blue-green deployments to help you manage your availability. It has lots of great features. Finally, we have everything running. We have it continuously deployed. One thing we still need is that observability piece we talked about at the beginning. We want to monitor our applications and make sure that they're working as expected. The standard cloud native tool for that is called Prometheus. We can deploy Prometheus into our Kubernetes cluster, and it's going to connect to all our applications and collect metrics from them. It can also collect metrics from our nodes, make sure they're running normally. It can collect metrics from Argo and make sure our continuous deployment is happening as expected. Prometheus also has a sidecar called Alert Manager, and Alert Manager lets us get alerts when things aren't working like we want them to. So at this point, we've used these cloud-native tools to reach our goal of having loosely coupled systems that are manageable, resilient, and observable. And that's great. The thing you'll notice is that you now have a lot of infrastructure. I've highlighted on this slide all of the components that are not your application. They're just the infrastructure that you need to run your application. And you don't want to spend your time managing that stuff. What you want to spend your time on is building your app. So this is where managed services from companies like DigitalOcean come in. First off, we have DigitalOcean Kubernetes. So you don't need to create your own nodes and set up the Kubernetes control plane and manage all of that complexity. We can do that for you. It's fully automated, driven from our control panel or our API. And this helps you handle both setting up a cluster and also day-to-day operations of it, like upgrades. We also have a managed container registry, so there's no need for you to run your own. This is private to your team, it's highly available, and it's fully managed. All you need to do is create a registry and then start pushing your images to it. No further management needed. Super easy to get started. Finally, we have these one-click applications for Kubernetes, including Prometheus and Argo, and lots of other great tools too. You will need to do some configuration of these tools for your specific use case, but we make installing them super easy, and they've been tested on DigitalOcean Kubernetes, so you know that their basic configuration will work with your cluster. At the end of the day, you've got all this infrastructure managed. You can focus on building your application, building your business. You get all of the benefits of cloud native. Remember, loose coupling that enables resilience, manageability, and observability without all the operational overhead of managing a bunch of systems. So now that we've seen what cloud native means and how Kubernetes fits into it, I have some great updates to share about our DigitalOcean managed Kubernetes product. First off, I mentioned earlier that we have a variety of one-click applications for Kubernetes. These are available in the DigitalOcean control panel and also in the marketplace at marketplace.digitalocean.com. All of these applications can be installed to a DigitalOcean Kubernetes cluster, either a new one or an existing one, with a single click or via a call in the DigitalOcean API. Using these one-click applications frees you from having to find and install these projects and configure them, make sure they work with DigitalOcean Kubernetes, helps you set up all of your infrastructure and get you up and running faster so you can focus on your own applications. As always, we have the 3 most recent minor versions of Kubernetes available, and they're certified conformant by CNCF. At the moment, that means 1.17, 1.18, and 1.19. A new minor version is released roughly every 3 months, and they're supported for 9 months by the upstream Kubernetes community. That means the 3 most recent versions are the ones that get updates and support, including security fixes. So we would highly recommend that all of our customers try and keep their clusters on these 3 supported minor versions. Upgrading is just one click, and we suggest you do it early and often. One thing you might have heard if you follow Kubernetes is that the upstream community will soon be changing to support their releases for a year instead of 9 months. When that happens, there will be 4 supported releases at a time, and we'll make that adjustment as well, offering 4 releases as soon as we can. Speaking of upgrades, we've made a major improvement in our upgrade process with the introduction of what we call surge upgrades. In our legacy upgrade process, we upgraded nodes one at a time, and we destroyed the old nodes before we created the new ones. This meant that your upgrade was really slow because we were going one node at a time. It also meant that you had reduced capacity in your cluster during the upgrade because we would destroy a node before we created a replacement for it. By contrast, in our surge upgrades, we'll upgrade up to 10 nodes at a time, and we create these 10 new nodes before we destroy the 10 old ones. This means that your cluster has some extra capacity during the upgrade. It ensures that we can always drain the workloads off of your old nodes safely. More importantly, it means your upgrades are much, much faster. So surge upgrades are a great improvement. They really will help your upgrades be much smoother, much safer, and much faster. Surge upgrades are currently an opt-in feature, so you will need to enable them for your cluster through the DigitalOcean control panel or the API. If you are using DigitalOcean Kubernetes, I would highly recommend that you do that. It's a much better upgrade experience than what we had before. I think it will really help our customers operate their clusters more efficiently. If you do want to make sure that you're always on the latest version, you can configure a maintenance window for your cluster and enable auto upgrades. This will mean you always get the latest patch version within the minor version that you're running right away. Things can change more between minor versions of Kubernetes. It's much more likely to break your workloads, so we don't apply those upgrades automatically. However, staying on the latest patch release within a minor version will make those minor version upgrades much smoother, much easier, and it will also ensure that your clusters always have the latest security patches, again, as long as you're within the 3 supported releases. One new feature for our auto upgrades is notifications. If you enable auto upgrades today, you will get notifications 1 week and 1 day before an upgrade happens. That'll help you plan your maintenance a little bit and also just serve as a reminder for your maintenance window. There are also a couple of security improvements to our Kubernetes product that I'd like to share. First off, DigitalOcean released the Virtual Private Cloud or VPC feature in April across our platform. And you can use VPC with your Kubernetes clusters. So you can now create multiple virtual private networks within a DigitalOcean data center, and you can create a Kubernetes cluster in your VPC. This lets you better isolate your infrastructure. For example, if you have a managed database in a VPC, you can create a Kubernetes cluster in the same VPC. They can communicate over that private network without the database being exposed to the internet or to any other VPCs you might have in the data center. Likewise, anything outside of your Kubernetes cluster's VPC, like a droplet or another cluster, won't be able to connect to the worker node's private IP addresses. This is just a nice bit of isolation, nice security improvement. Finally, with Kubernetes 1.19, we've made our clusters more secure by default than they were before. Every Kubernetes cluster on DigitalOcean is protected by a managed cloud firewall. In the past, we left the full range of possible Kubernetes node ports open on that firewall, so that if you set up a node port service, it would be available to the internet. Unfortunately, this also meant that if you inadvertently had a service listening on a port in this range on a worker node, for example, if you had a pod configured with host networking that you didn't intend to be public but was listening on one of those ports, it would be exposed to the internet too. In Kubernetes 1.19, we've started only opening the node ports that are actually in use by services on the cluster. This means that by default, your worker nodes are locked down completely firewalled off from the internet, and you have to explicitly create a service in Kubernetes or add an additional cloud firewall if you want a port to be available. This should give our customers a bit more peace of mind. It just means that your worker nodes are further isolated and you're only exposing what you want to expose. The other product I mentioned earlier is our DigitalOcean Container Registry, and today I have some very exciting updates about that. First off, the big excitement, our container registry is now a generally available product. This means it's fully supported, it's ready to be used in production, it's really polished, has some great new features. I'm excited about it. With GA, one thing that's changed is a new pricing model for our container registry. And this new pricing model includes a free tier. In the free tier, you can store one image repository, as many tags as you want, up to 500 megabytes of data. And this is perfect if you're just getting started with containers and cloud native, or if you're just starting on a new application, you don't have too much to push. When you do outgrow that free tier, we have a $5 tier and a $20 tier. These offer more repositories and more storage. All of the tiers are generally available and production ready. So this is a great simple container registry product for you to use. One of the big reasons that I mentioned we want to use container registries is to then deploy those containers into a Kubernetes cluster. We have made that super easy by adding a one-step integration between the two products. So rather than downloading credentials, creating secrets in Kubernetes through the command line, you can now click a button in the control panel and all the images in your registry are immediately available in the clusters you select. This makes it really, really easy to deploy your containers into your cluster. Using your private images is basically as easy as using public images. One last cool feature of our container registry is that it's not just a container registry, it's actually an artifact registry. So you can push things other than container images to it. This works with any tool that can use what's called an OCI registry. One example is Helm. This is an experimental feature in Helm at the moment, but if you enable it, you can push a Helm chart to a registry like the DigitalOcean Container Registry, and this mechanism will eventually replace the current concept of Helm repositories. Once that happens, and once tools like Argo are updated to support that feature, you'll be able to push all of your production artifacts, so both your container images and your Helm charts for deployment, to one place and deploy from there. This is really nice for keeping everything together and keeping your production artifacts separate from your development artifacts like code. This, again, is all in a stable repository that you're not managing yourself. It's a managed container registry. That's all the product updates I have for today. Before I go, I wanted to leave you with a few next steps as you start your cloud native journey or continue your cloud native journey with DigitalOcean. First off, our community team has put together a great curriculum about Kubernetes. It covers not only how to use and operate Kubernetes clusters, but also how to build the kinds of modern cloud native applications that we talked about earlier. If you are already a DigitalOcean Kubernetes user or container registry user, or if you're interested in trying out those products, I'd recommend you check out our documentation. Our documentation covers getting started with the products, as well as enabling new features like surge upgrades, and lots of information on how to complete common tasks with the products that you might want to do as you start to build your business. That's all I have for today. I hope that you'll try out DigitalOcean Kubernetes and Container Registry for your own cloud native workloads. And if you have any questions today, I'm happy to answer them in the breakout room for this session on Discord. Thanks very much. Enjoy the rest of the day.